There are several reasons why manufacturers don't universally produce terminals rated at 90 degrees Celsius. Firstly, cost is a significant factor. High temperature rated terminals necessitate the use of more expensive materials and more complex manufacturing processes. This naturally translates to a higher price point for the terminals themselves. Secondly, safety considerations play a crucial role. Terminals designed for 90 degrees Celsius operation might exhibit a higher propensity for failure when subjected to elevated temperatures. Such failures could potentially introduce safety hazards into the electrical system. Thirdly, compatibility presents a barrier. Many existing electrical installations are not engineered to accommodate terminals rated for 90 degrees Celsius. Integrating these terminals into legacy systems would necessitate potentially expensive and disruptive upgrades to ensure the system's overall integrity and safe operation. Despite these reasons, there are specific scenarios where the utilization of 90 degrees Celsius rated terminals can prove advantageous. For instance, in environments characterized by high ambient temperatures, or in situations where space constraints demand a higher ampacity within a limited footprint, these terminals can be beneficial. In such cases, the advantages derived from employing 90 degrees Celsius rated terminals may outweigh the associated costs and complexities. The prevailing 75 degrees Celsius rating for terminals is rooted in the assumption that these terminals will typically operate in indoor environments where the ambient temperature hovers around 30 degrees Celsius. When ambient temperatures exceed this level, it becomes imperative to derate the terminals. This derating process ensures that the terminals operate within their safe thermal limits and prevents them from overheating, which could lead to insulation degradation, conductor damage, or even fire hazards. The ampacity of a conductor is intrinsically linked to its physical characteristics, including its size, the material from which it's constructed, and the type of insulation that encases it. Employing a larger conductor, or one that features a high temperature rated insulation, directly translates to a greater ampacity, enabling the conductor to carry more current safely. If there are concerns regarding the ampacity of conductors in a specific application, a derating factor can be applied to reduce the conductor's allowable current carrying capacity to a level that ensures safe operation. This derating strategy mitigates the risk of overheating and potential fire hazards by conservatively limiting the current flow. Ultimately, the decision to utilize 90 degrees Celsius rated terminals is not a one-size-fits-all proposition. It necessitates a careful evaluation of the specific application, taking into account factors such as ambient temperature, load requirements, space constraints, and the overall design of the electrical system. This decision should be entrusted to a qualified electrician who possesses the expertise to assess these factors and make an informed judgment based on the specific circumstances. Consider the National Electrical Code, specifically Section 110.14. It stipulates temperature limitations for conductors. The intent is to prevent overheating at connection points. The equipment is judged based on its design and marked with conductor termination temperature ratings. Conductors must be selected and installed so that the temperature rating of the conductor is not exceeded. This article covers ampacity, temperature limitations, and other factors for electrical installations. Generally, the termination temperature is 60 degrees Celsius for equipment rated 100 amps or less, and for conductors size 14 AWG through 1 AWG. If the equipment is marked for high temperature rated conductors, the conductors can be sized based on the higher temperature rating. But the goal is that we don't exceed the lowest temperature rating of any connected termination conductor or device. For equipment rated over 100 amps, or for conductors larger than 1 AWG, the termination temperature rating is 75 degrees Celsius. Again, if the equipment is marked for use with higher temperature rated conductors, the higher ratings can be used. When selecting conductors, you will often find that higher temperature rated conductors have higher ampacities listed in the tables. However, the lower temperature rated terminations often limit the ampacity that can be used. It's important to understand conductor ampacity. Ampacity is the current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC tables 310.16 and 310.17 provide ampacities for conductors based on insulation type and ambient temperature. These ampacities are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, a correction factor must be applied to reduce the ampacity of the conductor. The ampacity is affected by the number of current-carrying conductors in a raceway or cable. When multiple conductors are bundled together, the heat generated by each conductor can raise the temperature of the other conductors. This requires a dilating factor to be applied to the ampacity of each conductor. For example, if there are 4 to 6 current-carrying conductors in a raceway or cable, the ampacity of each conductor must be reduced to 80% of its value in table 310.16 or 310.17. The insulation type of the conductor affects its ampacity. Conductors with higher temperature-rated insulation can carry more current than conductors with lower temperature-rated insulation. For example, a 12 AWG copper conductor with THHN insulation has an ampacity of 30 amps at 30 degrees Celsius, while a 12 AWG copper conductor with TW insulation has an ampacity of only 20 amps at 30 degrees Celsius. The location of the conductor affects its ampacity. Conductors installed in free air have a higher ampacity than conductors installed in raceways or cables. This is because conductors in free air can dissipate heat more easily. For example, a 12 AWG copper conductor with THHN insulation has an ampacity of 35 amps in free air, while it has an ampacity of only 30 amps in a raceway or cable. The size of the conductor affects its ampacity. Larger conductors have a lower resistance and can carry more current than smaller conductors. For example, a 10 AWG copper conductor with THHN insulation has an ampacity of 35 amps, while a 12 AWG copper conductor with THHN insulation has an ampacity of only 30 amps. The material of the conductor affects its ampacity. Copper conductors have a higher ampacity than aluminum conductors. For example, a 12 AWG copper conductor with THHN insulation has an ampacity of 30 amps, while a 12 AWG aluminum conductor with THHN insulation has an ampacity of only 20 amps. Consider conductor dilating. Dilating factors are used to reduce the ampacity of conductors when they are installed in conditions that are less than ideal. For example, dilating factors are used when conductors are installed at high ambient temperatures, when there are multiple current-carrying conductors in a raceway or cable, or when conductors are installed in wet locations. The NEC provides tables of dilating factors that can be used to calculate the correct ampacity for conductors in different conditions. For example, if a 12 AWG copper conductor with THHN insulation is installed in an ambient temperature of 40 degrees Celsius, the ampacity of the conductor must be reduced by 8%. The derated ampacity of the conductor is 30 amps x 0.92 equals 27.6 amps. When selecting conductors for an electrical installation, it is important to consider all of the factors that affect ampacity, including the size of the conductor, the material of the conductor, the insulation type of the conductor, the location of the conductor, the ambient temperature, and the number of current-carrying conductors in a raceway or cable. By considering all of these factors, it is possible to select conductors that are properly sized for the application and that will operate safely. Consider the practical implications of using 90 degrees Celsius rated conductors. While the conductors themselves may be rated for high temperatures, the termination points, such as breakers, lugs, and other equipment, often have lower temperature ratings, typically 75 degrees Celsius or even 60 degrees Celsius. In such cases, the ampacity of the conductor must be selected based on the lowest temperature rating of any connected termination conductor or device. This means that even if you use a 90 degrees Celsius rated conductor, you may not be able to take full advantage of its higher ampacity if it is connected to a 75 degrees Celsius rated breaker. The NEC specifies the rules for selecting conductors and terminations. Section 110.14c covers terminal connection temperature limitations. It states that the temperature rating associated with the ampacity of a conductor shall be selected and coordinated so as not to exceed the lowest temperature rating of any connected termination, conductor, or device. This ensures that the entire system operates safely and that no component is subjected to excessive temperatures. Consider high ambient temperatures. In environments with high ambient temperatures, the ampacity of conductors must be derated to prevent overheating. The NEC provides tables of correction factors that can be used to adjust the ampacity of conductors based on the ambient temperature. For example, if the ambient temperature is 40 degrees Celsius, the ampacity of a conductor must be reduced by 8%. In some cases, it may be necessary to use a larger conductor than would normally be required in order to compensate for the effects of high ambient temperatures. Consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 5% for power, heating, and lighting circuits, or 3% for branch circuits. To minimize voltage drop, it is important to use conductors that are large enough for the load they will be carrying. In some cases, it may be necessary to use a larger conductor than would normally be required in order to reduce voltage drop to an acceptable level. Consider conductor insulation types. Various insulation types are available for conductors, each with its own temperature rating and other characteristics. Some common insulation types include THHN, THWN, XHHW, and RHW. THHN is a thermoplastic high-heat resistant nylon-coated conductor with a temperature rating of 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. THWN is a thermoplastic heat and water resistant nylon-coated conductor with a temperature rating of 75 degrees Celsius in both wet and dry locations. XHHW is a cross-linked polyethylene high-heat and water-resistant conductor with a temperature rating of 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. RHW is a rubber heat and water-resistant conductor with a temperature rating of 75 degrees Celsius in both wet and dry locations. The choice of insulation type will depend on the application and the environmental conditions.